Okay. Good evening, everyone. Can you all hear me okay? Try that again. Can you turn the volume up on the microphone, Veronica? We'll try that again. Testing, testing. It was working about 10 minutes ago. Testing, testing. Can you hear that? Test, test. Is that better? Lovely, I'm getting some thumbs up. Okay, let's try that again. Good evening, everyone. Hello. It's my absolute pleasure to welcome you all to the planetarium here at Glasgow Science Centre. My name's Nina, I'm the planetarium coordinator, and very shortly I will be handing over to tonight's David Elder lecture speaker, Dr. Daniel Oy, who's joining us from the University of Strathclyde. It is thanks to the University of Strathclyde and the David Elder bequest that we're able to hold these lectures at all, so we're delighted to be working in partnership with them tonight. For those of us here in the planetarium, there's a few sort of logistical health and safety bits that I do need to get through. For those of you joining us on YouTube, we're delighted that you could be here. I'm sure you're aware of the health and safety situation in your own living room, so I will leave you to deal with that. So in the planetarium, during the lecture, we will be bringing the lights down, so it is going to get a wee bit harder to see. If you do need anything during the lecture or you want to leave, that's absolutely fine. You've got myself, my name's Nina, and we've also got my colleagues Veronica and Lawrence at the back. We'll be more than happy to assist. During the lecture, we do ask that things like phones, cameras, tablets get tucked away in a bag or in a pocket, just because the light can dazzle your eyes and the eyes of the people around you, makes it a bit harder to see what's going on the screen. You do get bonus brownie points if you can make sure those are turned to silent before you put them away as well. If anything exciting was to happen this evening, like a fire alarm, all the lights will come on. I get to put a really stylish high-vis waistcoat on. I will meet you at the back and lead you down some stairs into that slightly chilly Glaswegian evening. After the lecture, we will be inviting a bit of Q&A. We're looking forward to hearing from you tonight. If you do have any questions, do just pop your hand up. We will get those questions from you. Daniel will be repeating those questions so that people on YouTube can hear them. If folk on YouTube have got any questions, please do pop them into the chat box. Preface them with question in caps. It just makes it a wee bit easier for us to find them, and I will happily be the voice for you and ask those questions of Daniel tonight. But with all of the boring stuff out of the way, it is my absolute pleasure to welcome Daniel to the stage. So if you can join me in welcoming him, that would be wonderful. Thank you.
Hello, great. You can hear me, great. Thank you for that lovely introduction. Hopefully the lights can come down so you can see the screen. Yep, great. Yes, so welcome to this talk. So I'll be talking about the space quantum internet. And so I'll have to actually go a bit into quantum mechanics. I know you're here for the space stuff, but in order to understand why we're doing what we're doing and trying to put quantum technology into space, we need to understand something about the quantum physics. So we're really at the dawn of a new age of quantum technology. Some people have called this quantum 2.0, where we're exploiting the phenomena of quantum entanglement, of coherence, of superposition, in order to do things that previously we have not been able to do. The previous age of quantum 1.0 would be things like using lasers, which are obviously very, very useful devices, but don't really exploit the full capabilities of quantum mechanics. And I really want to take you back to just last year, and that is the 2022 Nobel Prize in Physics. And it was given to these three people, John Clauser, Anton Zeilinger, and Alain Aspect. And it was given, the quotation is, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. And this has been a big deal because people have been working on these fundamental ideas for ever since the beginning of quantum theory, and certainly since the 1930s. And it wasn't till about the 1960s when some people really became serious about trying to understand the meaning of quantum theory and its practical consequences. And so we go to back to the 1930s, and we've got these two people. You may recognize them. On the left is Albert Einstein, and on the right is Niels Bohr, two of the some of the greatest scientists of physicists of the early 20th century. Now, Einstein was actually one of the co-inventors of quantum theory, along with Niels Bohr. Niels Bohr very famously came up with a model of the atom using quantum principles, and Einstein famously discovered the photoelectric effect, or, well, explained the photoelectric effect in terms of quantum ideas. But they disagreed very much about the meaning of quantum theory. So, for instance, Einstein very famously says, God does not play dice. He didn't like the randomness in quantum theory. And Bohr very diplomatically said, Einstein, stop telling God what to do. And so they had these ongoing debates about the meaning of quantum theory. And really the essence of their quarrel was, Bohr was really saying about quantum theory that reality is indeterminate until you observe it. There's no underlying objective reality until you do a measurement. But Einstein, he obviously didn't like this. He said, objects have definite properties regardless of whether you actually measure it. Now, these debates happened throughout the early development of quantum theory. And in 1935, Einstein, with colleagues Podolsky and Rosen, wrote a paper and came up with a situation which seemingly demonstrated that quantum theory was incomplete. Not that quantum mechanics was wrong, but it wasn't the whole story, and that there was a deeper layer of explanation. And it wasn't really until the 1960s when John Bell, who born in Belfast but worked in CERN, he thought very deeply about these arguments and the meaning of quantum theory. And his great genius was being able to take the ideas and the position, the scenario that Einstein had presented, and really turn that into something that people could test. In the end, he said that Bohr was inconsistent, unclear, willfully obscure, and right. Einstein was consistent, clear, down to earth, and wrong. And that really sort of sums up that even though Einstein thought he knew the true situation of quantum mechanics, and Bohr was famously very unclear about what quantum mechanics meant, in the end, it turned out that Einstein was wrong, and arguably Bohr was right. On the other hand, Bell also said, I'm a quantum engineer, but on Sundays I have principles. How we interpret that is that sometimes we don't need to worry about what it means, we just need to calculate and just use the results and things work. But sometimes it's good to question the foundations and really ponder about the absolutely fundamental questions about physics. So I want to try to give an idea of what Bell's thinking was and why his Bell's inequality, his theorem, is so important, and what it says about the nature of reality. So we're going to take two prototypical players. So we've got Alice and we've got Bob, and they order some quantum gloves from a factory. And so these gloves, they order one each, and they're packaged as a pair at the factory, and they send one to Alice and one to Bob. And they want to ask, or they want to know, for instance, whether they got a left-handed or a right-handed glove, right? Now it's not clear that they've gotten one of each, or maybe got both left or both rights, but they can certainly ask the question of whether they have a left or right-handed glove. So they sort of ask the question, and the box reveals to them whether they've got a left or right-handed glove. They can ask for another set of boxes, and they ask the same question, they might get a different result. They can also, for example, ask a different question of what's in the box. For instance, what color is the glove, right? Now, these are quantum gloves, so you can only ask one question of the object at a time, and once you've asked that question, you only get the information about that question you asked. So you can't simultaneously find out whether it's a left or right-handed glove or whether it's a green or blue glove. So you can try this again and maybe get a different answer. And you don't necessarily, Alice and Bob, they're separated very far away from each other, and they don't talk much to each other. And maybe they're so far away that, maybe light years away, that they can't actually communicate. And so they randomly and independently decide what sort of question to ask. So sometimes they ask two different types of questions. So maybe Alice decides, is it left or right glove? And Bob asks whether it's a green or blue glove. Or they may do vice versa. So let's look at what Einstein would have thought about the situation. So consider the factory, it's making these gloves, and Einstein would say, these gloves, even though they're quantum gloves, they actually have, a handedness, the left or right, and they've actually got a color. So he would say, well, there are actually 4 different types of gloves, right? We've got blue left-handed, green left-handed, or blue right-handed, or green right-handed. And maybe at the factory, they package up these gloves in pairs in these 2 boxes, and maybe they package 2 left-handed blue gloves, 1 in each box, and send 1 to Alice and 1 to Bob. Or there could be a green and a blue, left-handed, and so on and so forth. So there are 16 possibilities of having, 1 glove in each box with definite handedness and definite color. So this is what Einstein would say, this is really what's happening at the microscopic scale, at the quantum scale. Things really actually have properties, even though we may not know it, and maybe quantum mechanics doesn't allow us to find out in one go what they are. So what Bell did was take this idea that things actually are real, and also the idea that because these 2 boxes are very far away from each other, and Alice and Bob can act independently, the choice of what question, say, Alice chooses to ask, cannot influence the outcome of Bob's measurement or observation, right? This is just due to special relativity. Influences can't travel faster than the speed of light. So the choice of what Alice decides to ask of her glove cannot influence the result of Bob's measurement. So these 2 things are called local realism, these 2 assumptions. And this is sort of the natural way that we think the world works. And this is what Einstein was saying really was happening underneath the whole machinery of quantum mechanics. So Bell took these 2 assumptions and said, well, really, how can we test this? Is this actually the real situation? So we go back to Alice and Bob and we say, well, what can they actually measure? Right? There are actually 4 different situations that they can measure, right? They can each decide to ask whether it's a left or right glove, or what color is the glove. And these are the 4 combinations. And if you work out the consequences of this very simple assumption that gloves have actual colors and actual handedness, irrespective of whether you measure them or not, and you can't influence things faster than the speed of light, then you find that this does not give you the right answers that quantum mechanics gives you. Right? Quantum mechanics actually give you correlations or patterns of results which are far more, that they're stronger than what you would get under the local realist assumption that Einstein was saying was the true situation. So the thing was that basically Bell showed that there was an observable physical consequence to what Einstein was saying, 30 years previously. And what Einstein was saying was actually not what quantum mechanics was saying. The actual experiments, if you were to do them, would give you different results based on what Einstein was saying and what quantum mechanics was saying. Now, ever since the 1960s, people have been working to try to find out, was Einstein or Bohr correct? And Clauser, the first of our Nobel laureates, was one of the first people to actually start doing experiments. Later on, Alan Aspect, he actually did some groundbreaking experiments which tried to show or try to rule out that influences could travel between the two boxes, in essence, faster than the speed of light. And then Zeilinger, he then actually tried using entanglement to do various things. He did quantum teleportation, as well as other protocols and applications using entanglement, and really brought forward the experimental utilization of these quantum effects. So let's go back to the idea of quantum entanglement, which was what they got the Nobel Prize for. So basically, quantum mechanics allows particles to have this property of entanglement, which means that pairs of particles, for instance, their fates are interlinked, so even if they're very far apart. So we can sort of visualize them as some, well, as Einstein said, some spooky action at a distance. Now, this property of entanglement actually is one of the defining properties or defining phenomena of quantum mechanics, and that's how it characterizes itself against what we would deem everyday physics of Newton, for instance. And this entanglement can be utilized for various things. And you may have heard about quantum computers. We can also use them for making much more accurate measurements. We can build quantum networks. For instance, if you've got lots of quantum computers, just like today when we use the internet to network normal computers, we can use quantum networks to network quantum computers and increase their power. We can also use them to secure quantum encrypted communication. We can use the properties of quantum states to make sure that people can't hack into our communications. So all of this is it's built upon the idea of quantum information. That information is encoded in physical systems. So classical information, for instance, like an abacus, normal computers aren't that much different from an abacus in terms of how they represent data in terms of definite states of a physical system. Whereas we know that quantum states can be more indefinite. So as Bohr said, the state of a quantum system can be in this delicate superposition of different possibilities. And when we network different quantum systems, they can all exist in this multitude of possibilities, and thus quantum information allows us to do quite a lot of things that you can't do when you have classical information. Ultimately, because information and data is stored in physical systems, how physical systems can be stored, can be transported, and can be processed or can evolve, ultimately tells us what we can do with information that they encode. How we can transmit information is exactly how we can actually send physical states, either physically through, say, matter or through light. So the phenomenon which we are trying to exploit is entanglement. So usually how entanglement is created is where, for instance, say you've got a blue photon, so this is a blue particle of light. We can basically split it in a process called down conversion into two lower energy photons, which basically can travel far apart but still be entangled. So the properties of one photon are determined by the other. Now, quantum properties are very fragile. Quantum states are very fragile in that it's very hard to keep them from interacting with the rest of the universe and essentially being observed. So if we've got a quantum system and we observe it, then some people would say the wave function collapses into a definite state. But this happens at random. So if you were to start off with another copy of that state, or another version of that state, and make the same measurement, you may get a different result. So this fragility of quantum information can actually be used in a process called quantum key distribution. So we can take our quantum states, and instead of using atoms, we can use, for instance, light, particles of light called photons. And if Alice and Bob want to communicate securely, they can send these individual photons, individual quanta, to each other. And Alice can prepare them, Bob can measure them, and if there's nothing in the way, they get a perfect communication channel. But if there is a nefarious eavesdropper on the line, if they try to eavesdrop, they try to tap into the channel, then they will disturb that state, and some people say collapse the state, and that means that Bob will find something, or when Bob measures the state himself, will find a different result to what maybe he should expect. So every time this happens, Eve can disturb the state, and Bob can get a modified result or a disturbed result. So in this way, Alice and Bob can actually determine how much tapping or how much eavesdropping actually has occurred, and then take steps to basically counteract that. And this is the basis of quantum key distribution. So this whole idea of using quantum theory to make our communication secure, so these are three notable names in the field. So there's Charlie Bennett and Gilles Brazard. They invented the first quantum key distribution protocol called the BB84 protocol, which people are now selling equipment that uses something very similar to that to encrypt information on optical fibers, for instance. Now, the reason why people want to do this is because the existing public key crypto system, public key encryption, is actually vulnerable to quantum computers should they be built sufficiently large and powerful enough. And this is all due to Peter Shor, who came up with his particular algorithm, which if you could have a large enough quantum computer, would be able to break conventional public key crypto systems. The other main person is Arthur Eckert, who actually showed how you can use entanglement in order to do this encryption. And this utilizes the fact that prior to measuring the states, there is no actual key or data to be hacked. So we can actually use the entanglement to guarantee that no one has tampered with it. So quantum communications really relies on the fact that we need to send these delicate quantum states. Now, usually we use optical fibers. So if we try to send a photon down a very long bit of optical fiber, it will actually get absorbed. This limits the range to only a couple of hundreds of kilometers at most without using an amplifier. But quantum states can't be amplified, not conventionally, so we can't actually send these photons directly very long distances. However, we can bypass an optical fiber. An optical fiber is just a very long bit of glass, and we know that glasses actually can absorb light quite a bit. If we send it through air, or even better, through vacuum, and we have some telescopes to send and receive them, so we can send them through free space. Free space can also include atmosphere. These photons can actually go very long distances. Every time you look up into the night sky and it's, if it's not cloudy, you can see stars which are light years away, maybe even millions of light years away. And those photons have traveled through the vacuum of space without being absorbed. So this is why people thought of using satellites and space in order to transmit these quantum signals over very long distances without trying to send them through optical fiber where it will be absorbed. So there were some initial ideas in around the year 2000 and maybe slightly before that. There were lots of people working on this initially, and there were some experiments to try to develop some of the technologies trying to do free space transmission through the atmosphere, although between two mountaintops. The higher you go, there's less atmosphere to get in the way, and also you need to get around the Earth's curvature. Obviously the horizon gets in the way if you're too low. So in order to transmit signals any appreciable distance, you actually have to go to quite high places. And so the pioneering experiment in this case was a 144-kilometer distance between two volcanoes in the Canary Islands, where they've actually got these observatories, these astronomical observatories, and they're able to transmit entanglement and demonstrate that they were entangled through violation of a Bell inequality over 144 kilometers. Now, this is a stepping stone to trying to do things in space. So people were trying to convince the European Space Agency to fund an experiment which would actually be put on the International Space Station. So here we see two twin beams. So these are pairs of entangled particles which are being sent down from the International Space Station to ground stations. Ultimately, European Space Agency decided not to fund further effort along this route. However, in the United States there wasn't that much activity, but if you go a bit east, a lot of investment was being made in China, and it was all due to this person, Jianwei Pan. He was actually the student of Anton Zeilinger, one of the people to receive the Nobel Prize. He went back to China with the experience, knowledge, and I guess passion from working with Anton, and he basically is now called the father of quantum, in China. And he was allowed the resources to really develop all sorts of quantum technologies, including quantum computers, but also quantum communication and space quantum communication. So they needed to basically reproduce or to obtain the same sort of knowledge of how to do this long-distance quantum transmission. So they did entanglement distribution over 100 kilometers, this time over a lake. They even put quantum transmitters and receivers on hot air balloons and showed that you could track an unsteady air vehicle like that. And they started building big telescopes. They're not big compared to some of the astronomical telescopes, but they're very big for doing laser communications. These things are about 1.2 meters in diameter. And obviously they need something to launch into space. So they started building a satellite. So this is called Messius, as part of the Quantum Experiments at Space Scale mission, or QUESS, but the satellite is called Messius. And so this is the final assembled version. It's about the size of sort of half a car, about the same mass as half a car. And once it was ready and they'd done all the testing and shown that the payload and all of the quantum experiments should work, they launched it. So that was in 2016. Now, the key point, the main experiment was to actually show that you could distribute this entanglement over distances far greater than 144 kilometers. Very hard to do that, to go further than 144 kilometers if you're restricted to the surface of the Earth. The curvature of the Earth is, one of the main things, but also trying to go horizontally through the atmosphere is difficult. So they actually were able to do this. So they built multiple ground stations around China, and they demonstrated that they could do it basically nearly 10 times further than had previously been demonstrated. So these are the ground stations. These are two of the ground stations. There were actually several. And we see these long exposure photographs of what it would look like if you were there when Messius was going over. Now, Messius has to simultaneously be able to transmit the photons down to both ground stations. On board, it had a quantum entanglement source which generated up to 6 million entangled pairs per second and sent them down. But because light beams, they're not infinitely narrow, they spread out, and also there is some bit of atmospheric absorption, a lot of the time these photons wouldn't make it down to Earth. If one of those photons did get to the telescope, but the other did not, then you would basically there's no entanglement being distributed. Occasionally, both photons would make it down, and this is roughly 1 pair per second. So you start off sending 6 million pairs per second, and more than there's a loss of more than 1 million to 1. And we only get 1 pair per second actually reaching both ground stations. But if we compare this to if we try to do this using an optical fiber, this is still 100 million times better. So if you had an optical fiber linking those two places over 1,000 kilometers, you would be waiting forever to try to actually receive any entanglement through an optical fiber. Obviously, we can improve things. We can use faster sources. We can use bigger telescopes. And we can optimize the whole experiment. And this is what people are attempting to do. So here's a video of an experiment where Messius is going over an observatory in Austria, in Graz. And so this just shows you what it looks like. So there's another satellite going over on the left. You can see the green beam, the red beam is what's being sent up to tell the satellite where the ground station is, and the green beam is another laser shining down onto the observatory to let the observatory know where the satellite is. But the quantum signals are actually invisible. They're infrared photons. They're roughly around 800 nanometers in wavelength. Now that was all sped up, so that would have taken roughly 5 to 10 minutes in total. But still a very short time to transmit these quantum signals, especially if a lot of them are lost. So what else did Messius do, or what else have the Chinese been able to do in the space with quantum communications? So they used Messius to act as a relay. So it could generate these quantum keys, these quantum encryption keys, between different places, and then essentially relay them, act as a trusted courier of these secret keys between places. And they famously were able to do a quantum encrypted video conference between Vienna and Beijing using Messius. So this was the first time that an intercontinental quantum secured communication video call was enabled. They were also able to use their space station. They were able to put another quantum signal source, a quantum sender transmitter, on that and show that they could use that. It was in a different orbit to the orbit of Messias, and therefore it was actually useful to know that these different orbits could be also used for quantum cryptography or satellite QKD. And the other thing they were able to do with Messias again was to conduct quantum teleportation. So what they did was they sent up entanglement from the ground to the satellite, and on the ground they were able to essentially use the quantum correlations in that entangled state to quantum teleport a state on the ground up to the satellite. Now, quantum teleportation, it's not quite like in Star Trek, but it is still a very, very important process that is used in all sorts of quantum information processing, including in computers, quantum computers. China's not stopping there. They've actually launched the second quantum satellite, Jinan-1. It's much smaller. It's 100 kilograms, not 650 kilograms. And because it's smaller, they can make more of them and they can launch more of them. So this one, the first one was launched in July last year. Not much news about how it's actually performing, but the hope is that they're going to launch a whole constellation of these things and use these in order to securely communicate across China and presumably around the world. So this sparked a quantum space race. Obviously, other countries were, sort of caught in the back foot on this. ESA had, not funded the pioneering work in trying to get quantum entanglement in space. The US seemingly wasn't interested in this. But shortly after the launch and success of Messias, there were a whole lot of other missions which were supported. There were some missions which were going on prior to Messias, but in the whole, Messias really spurred a lot of additional interest and funding. One of the biggest projects to come out of this renewed interest is the European Quantum Communication Infrastructure, or EuroQCI. And that is going to both use optical fiber quantum networks, but also satellite networks to connect the far reaches of the European Union. NASA wants to use the very long links between things like the lunar gateway and the Earth in order to test quantum mechanics. So the question is, how do we catch up? How do we catch up to all this effort, all this investment in this quantum space race? Well, we have to be smarter, right? So CubeSats are small satellites. They're cheaper to launch, develop, they're faster to develop, and they are a totally different philosophy to how space engineering has traditionally been conducted. So a CubeSat, the basic unit of a CubeSat is a 1U, and that's a 10 by 10 by 10 centimeter cube of roughly about a kilogram. But you can stack them together into bigger CubeSats. There are 2U, 3U, 6U, 8U, 12U, 16U. So basically you just take your building blocks and you stack them up into bigger satellites. But typically, they're roughly between 1 and 10 kilograms. I mean, these things are, this range is not strict, but this is sort of the sort of scale that we're talking about compared to the 650 kilograms of Messias. Even the 100 kilogram Jinan-1 is still considered, it's called a sort of a mini satellite or microsatellite. These CubeSats are called nanosatellites. Because they're so small and much cheaper to produce, we can launch a lot of them at once. So here is 101 CubeSats being deployed into space from an Indian launch vehicle. A lot of these satellites were actually deployed by Planet Labs. They do Earth observation using these nanosats, and they've launched hundreds of these into orbit. And they provide daily coverage of the entire surface of the Earth. Now here, in Scotland, and in particular Glasgow, there are actually many companies who actually are building these CubeSats. And outside of the US, Scotland actually is one of the biggest producers of CubeSats. So, with CubeSats in mind, I started working with experimentalists. I mean, my background is actually as a quantum theorist, so I actually never actually build anything. So I have to convince my friends to actually build satellites and payloads. So I was able to convince Alex, my collaborator in Singapore, to start working on how to miniaturize these entangled photon sources. So the question is, how do you take what would normally fit in a lab and shrink it down? And we're talking shrinking down to the size of a CubeSat, or smaller than a CubeSat to fit into it. So it's an iterative process until you get to a final design. You've tested it in the lab, you give it a good name, and hopefully this thing will produce entangled photons and you can put it onto a satellite. So this is a little explanation of how it works.
Let's look at the path of photons through the package. The laser emits blue photons. The arrows indicate their direction. Once in a while, a blue photon passing through the crystals is split into two photons, one red and one orange. The blue photons are sent into a beam dump, but the red-orange pair we send to detectors, separating them by their wavelengths. Now we zoom in to observe the entanglement generation. Photons in this experiment look like flying pancakes. First we see the phenomenon known as down conversion, which is what we call the process when one blue photon splits into the two lower energy red and orange photons. Our down-converted photons only come out entangled when we have two crystals in the design. We illustrate the entanglement here as a spooky cloud connecting the two photons, representing their shared quantum state. Remember that the entanglement persists even when the photons are separated.
So we built that, and it worked perfectly in the lab, but we need to take it out into the wide world and show that it will work in conditions that replicate that of space without going to the whole expense of actually launching it in the first place. We want to be certain that it will actually work unattended. So, this might be familiar. But we way before that, we were actually using high-altitude balloons. So the idea is that at very high altitudes, we call this near space because the temperatures are quite low, the air pressure is near vacuum, and the conditions are very much like that in low Earth orbit. And you have to build something which is robust and can actually operate perfectly without anyone twiddling with it. You can't really fit a PhD student into a nanosat. So we hooked up with some friends in Konstanz in Germany. There was a local school which was hosting the launch of the balloon, and a local TV station covering it. And we basically set it all up. We inflated the balloon. It's a long process. You have to get all the wind conditions right, the meteorological conditions. And in front of the whole school, we launched it. Right. Up it goes. So it goes up into the sky. It has a radio transponder on it. And so a lot of these high-altitude balloons, they're launched by amateur radio enthusiasts, ham radio. So we could track it, and we tracked it across the border. So it actually went across the border into Switzerland. So we had to hop into the car, get onto a ferry, cross the border, and basically chase it down. And basically do a bit of radio hide and seek. So we actually need to figure out precisely where it was using a radio, a directional radio antenna. Eventually, we found it. The balloon had popped. It descended. It had a very small parachute which slowed it a bit, but basically it still descended at quite a rate. Hit the ground and it stuck because of, on one of its antennas, and we recovered it. But the end result was that it worked. It survived. It performed perfectly. So this wasn't the only one we did. There was another one we did, which we've published the results. And our thanks really go to Christoph, who ran the balloon launchers. So next thing is to put it on a rocket. So we need a satellite to put our payload in, right? So our payload is about 10 by 10 by 3 centimeters, and we only need a small satellite for that. And so we put it on GOMX2 by GomSpace, which is a Danish company. This is the size of it. So you can see specs, which is a tiny fraction of a small satellite. And we tried launching it.
5, 4, 3, 2, 1. And we have liftoff of Antares, the torque-free mission that brings Cygnus on its third CRS mission to the ISS. Got main engines at 108%.
Avionics power nominal.
And launch team, be advised, stay at your consoles. Everyone in the LCC, maintain your positions in your consoles. In the LCC, maintain positions at your console.
It was not a good day. We were feeling pretty down at that point. That's a picture of the fireball. My experimentalist colleagues, they saw the upside of this. They wrote a paper. That's what you do. And they released it on the 1st of April, 2015. It was about extreme environmental testing of a rugged correlated photon source. So, they write, well, we built it, we think it would have worked, but, we had this rapid unintended disassembly event to test it, and we hope that in the future we don't need to test it in this way again. But miracle, they recovered the cargo section of that rocket, and it was nearly intact. They were able to unload the cargo, including our satellite, and return it back to GomSpace, who turned it on, and it worked. They were able to run the experiment, and basically, it performed nearly the same as it did before we tried launching it. There was slight degradation in terms of one of the components, but not in the actual down conversion process itself. So what do? You do it. You do it again. You try again. So we found another satellite built this time by NUS. Again, we tried again. This time it worked. So this is on an Indian rocket, and it worked. We showed that our payload would work in space. But it didn't actually have the full type of entanglement that we wanted, so we needed to launch a new version. So Spooky 1 was the next one we launched. We got the hang of things, right? So we were able to take our design of our experiment, make our own CubeSat this time, send it to Japan this time to be inserted into their P-pod, then basically send it up to the International Space Station, where they put it on the end of a giant robot arm, which they called affectionately known as the CubeSat cannon, and launch it out into space. This video isn't actually of the satellite, of our satellite. It's of 2 other satellites, but this is the picture of our satellite in orbit. And it worked perfectly. We're actually able to do some stuff about radiation. We're able to figure out how the radiation was damaging the equipment on board, particularly the single photon detectors which are used to characterize the entanglement. We're able to simulate that on the ground with very high resolution and actually confirm that the results in space correlated very well to how we actually modeled the effect of radiation on that satellite. But we want, the entanglement was generated on board. We would need to send these signals out. So we came up with a proposal to do this called the CubeSat Quantum Communications Mission, CQCOM. Again, this was not funded by the European Union. Seems to be a running theme here. But it did spur on many different daughter projects by individual countries, some of them which are successful, so Spectre, Cube, Spectral have a second satellite they're going to launch. The UK is actually building a CubeSat to actually do this kind of transmission of quantum signals from space to ground. Canada have their own independent mission called KeySat, which we're actually contributing to. And I'm sure there are a lot of others which I've missed. But what's happening here in Glasgow? So we have a Scottish quantum CubeSat. I think you can see a model or a prototype in front of me here. It's built in the Clyde, literally. This is the man responsible, Steve Greenland, who used to work for Clyde Space and actually responsible for basically building or assembling UK's first official CubeSat that was launched called UCube-1. He since created a new company called Craft Prospect, and they've got a mission called ROCS, which stands for Responsive Operations for Key Services. So what we've done is that we've used all the experience in the prior missions and things like that. Steve has been involved in the prior work. We've worked with companies such as the Fraunhofer Institute to create space telescopes, miniature space telescopes, which can fit into such a small satellite, assemble them with other components, create quantum sources together with the University of Bristol, assemble them into complete payloads, assemble them into something that you can see in front of me, together with the ground station. We need something on the ground to receive these quantum signals. And what we've done is try to build small ones that you can take around and hopefully dodge the clouds. So this is the one that we've actually building. This is from a few years ago, and we've taken out and actually done some tests. And we've tracked the International Space Station. You can see that going over the sky. It's illuminated by sun. It isn't actually sending anything down. But of course, China has beaten us to it. They've created this mini OGS and used that to communicate with Messias. So, what does the future hold, right? So what I've shown is really the beginning of a journey, beginning of how we can use these small satellites to do this, space quantum technology demonstration and space quantum communication. So, we're looking at really encompassing the world with these satellites to distribute this quantum entanglement to create this space quantum internet. So from small beginnings, from these tiny satellites, these tiny payloads, we can think of building up to things like quantum memories and quantum repeaters. Quantum memories are things which can store and buffer quantum information and really enable these space networks to work more efficiently. And we can think of talking to other things, not just big ground stations, but say to aircraft or ships. And China also has done things like use drones to relay quantum entanglement around cities and things like that. So, this is sort of the vision, right? We have networks which are connected by quantum links. We've got satellites which can connect cities, connect countries, and also connect each other. So this is a little animation of worked with Airbus on how we could design such a space system, such a space constellation. So what we have here is aircraft. These blue cones are basically the footprint of a constellation of satellites which can talk to these aircraft. And so when the aircraft go within this blue cone, it can actually talk to the satellite and actually communicate via quantum signals. And then these satellites can then talk to these bigger satellites in this ring around the Earth and relay the quantum information, the quantum keys around the world. Right. So I'd like to end about what we're trying to do to create this future. And so there's, I run what's called the International Network in Space Quantum Technologies. This is funded by the UK Engineering and Physical Sciences Council, and it's to promote cooperation, international cooperation in space quantum engineering, and eventually advance development of the space quantum internet. And as you'll see, it is a very varied and international group who've come together, and hopefully I'll see maybe some of the young people in the audience in such a picture in the future. Thank you.
Thank you so much, Daniel. That was brilliant, and I'm glad you were able to find a silver lining in the rapid, unscheduled disassembly of that rocket. We do have time for a couple of questions from the audience. If you're watching at home on YouTube, remember, do just pop it into the chat, and I will read it out for you. If you can bring the lights up just so we can see our lovely audience, so we can see any hands up. So if you do have any questions, do pop your hand up. We're more than happy to take them.
Stunned silence.
Quantum physics does that to people. It's entirely understandable. Right down the front.
Thank you. So the secure keys will become useful at a certain point to protect our networks. When do you think that point will be, and why?
All right. So this is the question of when do you think this quantum key distribution might be needed to protect it against, say, the quantum computing attack, right? So the basic background is that quantum computers, they can run this Shor's algorithm, and this Shor's algorithm can break what's called public key encryption, which really is the sort of the underlying method by which we do the initial authenticated or cryptographic communication on the internet. So when you're talking to your bank, these algorithms, these cryptographic algorithms, are used to secure that initial link. And so quantum computers could break that encryption, and therefore anything you send today, if it's stored, could be decrypted later. So depending on the type of information that you're sending now, if that needs to be secret in 10, 20, 30, 50 years' time, I mean, think of medical data, right? That kind of data has a very long secret horizon that you want to keep it secret. Quantum computers, even if they aren't available, say, until 10 years from now, if you've got information which needs to be secret beyond that horizon, you need to start sending it in a way that could not be decrypted by quantum computers, which may exist within 10 years. And I think 10 years is not an unreasonable timeline to think that quantum computers might be big enough in order to actually run Shor's algorithm and decrypt this kind of secret information.
Thank you. I'm afraid we are probably going to have to wrap up at this point.
Yeah.
That was a phenomenal lecture.
Yeah.
Thank you so much. In just a second, we are going to be opening the same door to the one you came in. You can head off through the space zone and out into that Glaswegian evening. But before we do, I would ask you all to join me in saying a massive thank you to Daniel for delivering the first David Elder lecture. You can also grab some craft prospect stickers and some leaflets from Veronica on your way out as well. So do grab those as you go. We'll just go and mute